In this video, we're going to solve systems of nonlinear equations in two variables. Number one, we're going to recognize systems of nonlinear equations in two variables. Then we're going to solve nonlinear systems by substitution. We'll solve nonlinear systems by addition, and then we'll solve an applied problem using systems of nonlinear equations. What makes a system of nonlinear equations? A system of two nonlinear equations in two variables is also called a nonlinear system. It contains at least one equation that cannot be expressed in the form ax plus by equals c. So at least one of the equations is not a line. A solution of nonlinear systems in two variables is an ordered pair of real numbers that satisfies both equations in the system. The solution set of the system is the set of all such ordered pairs. So when you're solving a nonlinear system, you may have a solution set that contains more than one ordered pair. As with linear systems in two variables, the solution of a nonlinear system, if there is one, corresponds to the intersection points of the graphs of the equation in the system. So if you have a nonlinear equation, such as a parabola or a circle or an ellipse, you could intersect in more than one point. For example, if you have a parabola and a line. So I'm just going to draw a parabola. And I have a line, I could actually intersect in more than one place. So you can have more than one ordered pair as a solution. So let's solve this first system of nonlinear equations, and we're going to use substitution. Again, what makes this nonlinear is the top equation. The top equation is not a line. As a matter of fact, it is a parabola. And we know it's a parabola because of the x squared. So solving this by substitution means I need to either solve the top equation for one variable and substitute into the second, or I can solve the second equation for one variable and substitute into the first. And it doesn't matter which one you choose to do. You can do whatever you want. So for example, in the first equation, I could fairly easily solve that first equation for y. So I have x squared equals y minus 1. So I could add 1 to both sides. And then on the left-hand side of the equation, I have x squared plus 1. And that's equal to y. So now I could substitute this value for y into the second equation. And I need to be careful because I have a minus outside that y. So I need to be careful that I change the sign of everything. So let's see, we got 4x minus y equals negative 1. And I'm going to plug x squared plus 1 in for y. And I'm going to do that and make sure I put parentheses around it so I can make sure I don't have any sign errors. So let's do this up here. I have 4x minus x squared plus 1 equals negative 1. Now I need to distribute that negative across everything on the inside of the parentheses. And when I do that, I always change the sign of everything on the inside of the parentheses. When I distribute a negative 1 across, change the sign of everything on the inside of the parentheses. So I get 4x minus x squared minus 1 equals negative 1. And this is a quadratic equation. So I need to get it in a standard form so I can solve it either by factoring it or using the quadratic formula. So I'm just going to rearrange. And I'm going to add 1 to both sides. All right, so this is a quadratic equation I can solve by factoring. As a matter of fact, I don't think I'd want to use the quadratic formula on this. However, if I did use the quadratic formula on it, A is the coefficient on the x squared, B is the coefficient on the x, and C is 0 here, because when I added 1 to both sides, I got 0. So you could use the quadratic formula. I'm not going to. It's just a little bit more work than I'm willing to do. So I have negative x squared plus 4x equals 0. And the only thing I can do here is factor out an x. So I'm going to do that. Make sure I did that correctly by distributing the x back across the stuff inside the parentheses. Make sure I did it right. Negative x squared plus 4x. So I'm good to go. Now I have it factored. I'm going to set each factor equal to 0 from the 0 product principle. Subtract 4 from both sides. I get negative x equals negative 4. So I'm going to divide by negative 1. And I get x is 4. So I get x is 0 and x is 4 are the first coordinates of 2 ordered pairs that's a solution to this system. So this system of nonlinear equations has 2 solutions, 2 ordered pairs. So I have x is 0 and x is 4. Now I'm going to back substitute into one of the equations and solve for y. And I can use either equation that I want. I solved that first equation for y so that I could substitute into the second equation. So I solved for y. Y is x squared plus 1. So I can substitute the 2 values of x into this equation and find the y coordinate. All right, so the first one, when x is 0, I get y is 1. So that is the first ordered pair that's a solution to the system, 0, 1. Now I'm going to substitute 4 into that equation. Four squared is 16. 16 plus 1 is 17. So the second ordered pair, x is 4 and y is 17. So my second ordered pair is 4, 17. So my solution to this system of equations is the 2 ordered pairs, 0, 1, and 4, 17. Now I encourage you to take your TI-84 graphing calculator or 83 and graph these 2 equations. So you would have to solve the second equation for y, and you can graph that on your TI calculator. And you can see that these 2 graphs do intersect, and they do intersect in 2 places. And those 2 places are 0, 1. So x is 0, y is 1. So that would be on the y-axis. And then it also intersects at 4, 17. All right, let's solve this system of equations, but this system of equations begs for us to use some other method besides substitution. We're going to use addition, because to solve either one of these equations for x or y is way more difficult than I want to do. But if I use addition, the method that we learned earlier in the chapter, I can eliminate one of the variables. For your information, the graphs of these 2 equations are ellipses, and ellipses are kind of flattened out circles. So they look something like this. That's probably exaggerated, but something like that. They're ovals, if you will. And if you have 2 ellipses, which you do, they could intersect at 4 different places. So let's draw another ellipse over the top of this one. And you can see that it is possible for these 2 ellipses to intersect at 4 ordered pairs. So anticipate that you can get 4 ordered pair solutions. So 4 solutions, all ordered pairs. All right, so we're going to use addition. So as you recall, in addition, you're going to multiply 1 or both of your equations by a constant so that when you add the two equations together, you eliminate one of your variables. So for example, you could eliminate x. You could multiply the top equation by -4, both sides. And you could multiply the bottom equation by 3, both sides. And when you do that, you eliminate the x's because the first equation, x will be -12x squared. And in the second equation, it would be 12x squared. And when you add those two equations together, you're going to eliminate the variable x. So you could do that. You could also eliminate y. You could multiply the top equation by, I don't know, -3, both sides. And to eliminate the y, you would need to multiply the bottom equation by 2, both sides. Remember, when I multiply an equation by a constant, I must do that to both sides of the equation so that the equation continues to balance. All right, so we have 2 times 48. And when I do this, I'm going to get -6y squared, and I'm going to get 6y squared. And when I add the two equations together, I'm going to eliminate the y, and I'm going to be left with x. And either one of these works fine. It really doesn't matter which method you use. Just pick a variable to eliminate and multiply by an appropriate constant to eliminate that variable. I think I'll go with the second method because that's what I've done before and that's what's in my notes, so why not? So what do we get? -9x squared minus 6y squared. And my calculator tells me that -3 times 35 is -105. Then I get 8x squared plus 6y squared equals 2 times 48, which is 96. I add those two together. I get -1x squared equals -105 plus 96 is -9. And I do need to divide both sides by -1. And I get x squared equals 9. All right, so I'm going to go to the new slide here. X squared equals 9. Now to solve this, this is a quadratic equation. And you can solve this by subtracting the 9 from both sides and then factoring it. You could do that. I'm just going to take the square root of both sides. When I take the square root of both sides, I have to put the plus or minus in there. Remember, there are two numbers you can square and get 9. One of them's positive and the other's negative. You can always square two numbers to get a positive number. One negative, one positive. So what do I get? Plus or minus 3? So x can be 3 or x can be -3. Now I need to find y for those two x's. And I'm going to pick one of the equations and I'm going to plug in x and solve for y. And I chose the first equation because it was first. So I have x squared, see, what do I have? 3x squared plus 2y squared equals 35. That's my first equation. And I'm going to need to plug in x equals 3 and solve for y, and then plug in x equals -3 and solve for y. Now, if I plug in +3 or -3, I'm going to get the same two y values. And let me just show you how that works. So let's try x is 3. Let's put that up here. All right, so we're going to plug that in. So I get 3 times 3 squared plus 2y squared equals 35. 3 squared is 9. 3 times 9 is 27. So I have 27 plus 2 y squared is 35. I'm going to subtract the 27 from both sides. And I have 2y squared equals, I believe that's 8. Divide both sides by 2. Y squared equals 4. Take the square root of both sides. So y is plus or minus the square root of 4, which is 2, plus or minus 2. So the two ordered pairs I get from this is that x is 3 and y can be -2. X is 3 and y can be +2. So I get two ordered pairs from x equals 3. When the x coordinate is 3, I get two different y values. All right, now we're going to plug in -3. And when I plug in -3 for x and I square it, I get +9. So I get exactly the same equation I got before. So when x is -3, y can be 2 and -2, exactly the same results. Because when I square x, it's positive. So I'm going to get the same result for the two y's. So now when x is -3, y can be -2. And when x is -3, y can be +2. So the solution set to this system is a set of 4 ordered pairs. Now you can't graph this on your calculator. You could graph it on Desmos.com if you wanted to take a look at what this looks like, because it is 2 ellipses and they do intersect in 4 different places. They intersect at 3, -2. They intersect at 3, 2. They intersect at -3, -2. And they intersect at -3, +2. All right, let's solve an application using a system of nonlinear equations. Find the length and width of a rectangle whose perimeter is 20 feet and whose area is 21 square feet. Now we've been doing rectangle problems all semester long using perimeter and area. So you should by now know what the perimeter and the area of a rectangle is. So I always like to draw a picture. And it really doesn't matter if I let the length be x and the width be y or the other way around. It really doesn't matter. All right, so what is the perimeter formula? Perimeter says that is the measure all the way around the rectangle. So it's 2 times its length plus 2 times its width. So it's 2x plus 2y. And that, they tell me, is equal to 20. They tell me the perimeter is 20. So I could divide both sides by 2 just to make that equation a little bit easier for me to manage. Now, if I can write it down correctly. So x plus y equals 10. So there's my first equation, and it is linear. Well, what's my second equation? Well, my second equation is for area. An area of a rectangle is its length times its width. And they tell me that is 21. So now I have a system of nonlinear equations. I have x plus y equals 10 and xy equals 21. So now I need to solve that system of nonlinear equations. Now, if it's me, I'm thinking that I'm going to solve the top equation for either x or y and substitute. So I would solve this using substitution. I'm not even sure that there is a way to use addition to solve this. If there is, it's beyond my knowledge. So I'm going to use substitution, and I'm going to solve that top equation for x. Why not? And I'm going to do that by subtracting y from both sides. Now I'm going to plug that in, substitute that in to the second equation, which is xy equals 21. So I'm going to plug this in right there for x. So I get 10 minus y times y equals 21. And I'm going to, anytime I have an equation that contains parentheses and I want to solve it, I need to remove the parentheses. So I'm going to do that by distributing the y across. And it looks quadratic to me. So if it were me, I would probably subtract the 21 from both sides. And rewrite it. And then I would multiply both sides by -1, and it's just going to make it easier for me to factor. So just change the sign of everything. And it looks to me that this factors y minus 3, y minus 7. So if I set each factor equal to 0, y minus 3 equals 0, and y minus 7 equals 0, it looks to me like I'm getting y is 3 or y is 7. And so what's that mean? That means this is a 3 by 7 rectangle. You might have been able to figure that out by just looking at it. But a 3 by 7 rectangle is going to have an area that's 21, and its perimeter is going to be 3 plus 7 plus 3 plus 7, which is 20. And that is the end of section 5.4 on solving systems of nonlinear equations.